So as you can see here, each layer is connected by a weight matrix theta1, theta2 and so on. And then we apply the activation function A1, A2 up to AM, which is given in the hidden layer denoted by the orange circles. So activation function is applied to perform non-linear operations to move to the next layer. As I said, we have a weight matrix here in every layer. So we use different weights for calculating each of the neurons. We will see this in a while, how we use weights to calculate the neurons. But before that, let's understand what is an activation function. Now the activation function here is a sigmoid function. The equation for activation function is shown here. Here thetas are the weights. So there are many activation functions available, and its choice affects the performance of the model. There is one more common function known as ReLU function, which can be used as an activation function. Anyways, for now we are using sigmoid function. So let's see how do we find it for each of the neurons. So this is a neural network. The bias unit in the input layer will always have a value of 1, so we don't have to calculate it. Then the value of activation function for the input layer will be equal to the features. So again, we don't have to calculate the neurons of the first layer. Now for the next layer again, the bias neuron will have the value equal to 1. And then to calculate the activation function for hidden layer, we will use weights as shown here. Now as you can see, to calculate the first neuron of the hidden layer, we are using all the neurons of our previous layer, which happens to be our input layer. So all neurons of previous layer will be used to calculate all the neurons of the next layer. So the value of neuron can be calculated using the sigmoid function as given here on the screen. Just multiply the weights with each of the neurons of the previous layer and then add it and then use the sigmoid function. This way we'll get the neurons in the hidden layer. Similarly, to calculate the mth neuron of the hidden layer, we will multiply the respective weights with the neuron of the previous layer. So as you can see here, we have multiplied the weights with the neurons of the previous layer and then took the sum of it and then use the sigmoid function. So this way we can calculate all the neurons of the hidden layer. Now the next task is to calculate the weights. And we will have to calculate those weights that are optimum. So we will see in the upcoming slide how can we calculate the optimum weights. But that is how you calculate the neurons of the hidden layer. Now once all the neurons are calculated, we can write it in the form of vector as shown here. So you can see that each of the neurons from previous layer is contributing to calculate the activation function for each of the neurons in the next layer. Also, as I said earlier, the weights used in calculating each of the neurons are different. So in every layer we have a weight matrix that is to be calculated, and then we will use that weight matrix to calculate the neurons of the next layer. So that is how neural network functions. And obviously we will not be doing this manually. But this was just to give you an idea to explain how neural network do the calculations. Now coming back to the calculation of weights. So as I said earlier, we have to find those weights that are optimum. So let's see how we can calculate those weights. Now weights are nothing but coefficients. So we must have a cost function to guide us to calculate the best possible weights. So as you can see on the screen, the cost function is similar to logistic regression function with some modifications. Now you can have a look at it. All the notations are given here. Well, to be frank, it looks a bit scary, so I'll not be going into details. But just understand that the entire cost function is similar to logistic regression, and we have just added a regularized parameter. Hence, this is called as regularized cost function. Now refer to the note given here. It says that regularization is a technique used for tuning the function by adding an additional penalty term in the error function. The additional term controls the excessively fluctuating function such that the coefficients don't take the extreme values. That is the basic purpose of regularization parameter. So this was the cost function of neural network.